Hey guys, this is John with Far From Standard Tutoring. In this video I'm going to explain electrophilic additions, or EA for short. So the general theme you will see for EA is something like this. An alkene, which has one pi bond, so we're becoming a molecule with two sigma bonds. And so really electrophilic addition deals with pi bond chemistry, where the pi bond acts as a source of electrons. So you'll see that alkene reacting against reagent, such as something that has an electrophilic site and a nucleophilic site. So that just means electrophilic is just something positive in nature. Nucleophilic is something negative in nature. And you'll see that when both these add, they add as two sigma bonds to the final molecular structure like that. So what can be these electrophiles and these nucleophiles? Well, with electrophilic additions, you're mostly going to be looking at things that are strong acids, so pKa is less than 0, such as this, like the hydrobromo or the hydrochloric acids. These halogens with the hydrogens next to it. So the H acts as the electrophile, and the X, or halogen, acts as a nucleophile, something negative in nature. You can also see things with water and a strong acid catalyzing it. So the H again will be the electrophile, and the OH adding is the nucleophile. Let's take a look at two examples where we're having an alkene react against these reagents. The H will be adding, and then the nucleophile, whatever that is adding second. So what happens in electrophilic additions, we have the starting alkene here. Just for a reminder's sake here, when you have an alkene and I write an R, that just means it's going to be an R group or another carbon there. So just keep that in mind. So the first thing that happens with electrophilic addition is that this double bond is doing something. It's a source of electrons that's going to be moving. It's going to act as a door, as we like to say, and opening up to bond with that H there. So just imagine that this door right here, this double bond, is opening up, okay, to grab this H, which it does right here to form this intermediate step. And because it opens up, it leaves the second H there, or the second carbon there. It's no longer going to be bonded to the original carbon. You're going to form a carbocation right here. That is the intermediate, the carbocation intermediate. The second thing that happens is because that H was taken, the X is now floating there, X minus, it's our nucleophile. That's going to add to the carbocation site to form now this final product where the H is still attached, the original H from this acid, and now the X is attached to that second carbon. Because we no longer want that carbocation, the X that was there in the intermediate step now adds to this carbon to form the final product. And you'll see that we started with a double bond here, a pi bond, and now we have two sigma bonds present. You'll notice that both these carbons are essentially the same in this example. One carbon is attached to an H, and it's attached to an R as well. But what if we have two different carbons? A carbon that maybe is attached to an R and an H, but the second carbon is not the same, it's attached to two H's. There's a difference in these carbons, and therefore there's a difference in what's going to form in the intermediate step. We call it regioselectivity. So if we have a difference like this, the opening of this pi bond is actually going to be different. It's going to want to open to leave the most stable carbocation present. So the most stable carbocation that's going to form is the one that's going to be higher in the numbers of carbons that's attached to. So a secondary carbocation will form more so than a primary carbocation. A tertiary one will form better than a secondary. So in this case here, this carbon here is essentially a secondary carbocation that would form. If this were to open up, it's attached to two other carbons, so it would be a secondary carbocation. If this were to open up and this be the carbocation, it'd only be a primary. That's not going to want to happen. So the double bond here is going to open up this way to leave this carbocation present because it's going to be a more stable one because it's secondary. And that's what happens in this first step. Again, the double bond is opening up to grab the H, and it's forming this intermediate right here. As you see, the carbocation is secondary. This is going to be the major regioisomer that's going to form and produce this product. So keep in mind that if the two carbons are the same, it doesn't matter. There is no regioselectivity. The double bond is going to open either way, essentially, because they're both the same, to grab that H and form the final product. But if the two carbons are different, there's regioselectivity. The more stable carbocation is going to want to form, and so the major product will be something like this to follow along the lines of that major product based on that carbocation. Okay? So electrophilic addition, you're going to see a general theme like this with the alkene going from a double bond to two sigma bonds, and then taking into account what the electrophile and the nucleophile can be, because it's always going to be something strong acid base. Okay? The H adding, then the X or the OH, something negative in nature, that's the nucleophile. So I hope this was of help to you, and thank you for tuning in to Electrophilic Additions.